Hello, my name is Marissa Iraca and I'm from Lock Haven University. Today I'm going to be talking to you about machine learning with quantum dots data. This is a research project that I got to take part in this past summer through Brigham Young University. I'd like to thank my advisor, Dr. John Colton, and of course, the National Science Foundation for funding this research. The purpose of this research, simply put, is that in biomedical settings, there aren't enough accurate temperature sensing probes available. For example, whenever you're reading the temperature change that can cause a DNA sequence to unravel, sometimes this temperature change is too minute to even be detected. So we thought instead of reading the temperature directly, why not read the temperature indirectly by recording photoluminescence data from quantum dots as a function of temperature? Quantum dots are semiconductors, but they're only nanometers in size. Because they're so small, they have a large surface to volume ratio that help result in the bright and strong photoluminescent properties that we get from the quantum dots. And you can see in this picture here that quantum dots in a solution have a very bright and sort of neon color, which is pretty but also useful. The specific type of quantum dots that we use in this research are cadmium telluride, and they emit at about 809 nanometers. We're recording two types of data from the quantum dots. We're recording the spectrum intensity, which is how bright do the quantum dots glow at a given temperature, and also the optical lifetime decay. So how long does a photon live after it's emitted from the quantum dot sample? And the way that we get a photon to be emitted is through this setup here. We start with the pulse generator, which starts the TCSPC module. TCSPC stands for Time Correlated Single Photon Counter. Simultaneously, it also starts the laser diode, which sends pulses of laser beams onto our quantum dot sample. Within our quantum dot sample, electrons are excited to a higher energy state, but since they don't want to have all this energy, they return back to ground state and emit photons in the process. The photons are then directed by a lens towards a set of filters. We use multiple filters to get rid of any excess noise from the laser beam and also so that only one photon passes through since we're trying to record the lifetime of a single photon. This photon is then directed by another lens towards a spectrometer, which is set for the peak wavelength of the quantum dot sample. And then the photon is directed towards the PMT, which stands for photomultiplier tube, and the PMT is used to stop the TCSPC module. Then we get a couple graphs that look like this. This is normalized data, which just helps put it all to the same key, which makes it a little bit more comparable. This graph here on the left is the spectrum intensity data, and we can see that the peak of this wavelength occurs at 809 nanometers. And I had just said that we're using cadmium telluride quantum dots which their peak wavelength are 809 nanometers. So this is good. This is what we expect to see. And this is the time resolved data, which is the optical lifetime decay. And we can see that this data drops off as a function of time exponentially, which is also a function that you would expect to see for optical lifetime decays. Then we take this data and apply it to machine learning. This is the part that I got to help out with this past summer due to COVID and being online. We all know the story of that. I got to write the code of a neural network that will accept the photoluminescence data and output a temperature prediction. But before I got to write the code, I had to learn a little bit about it. And so this is a nice picture of what a neural network is. Neural networks get their names inspired from the neurons in your brain, which spark, make all these different types of connections. Similarly, a neural network contains multiple layers and multiple nodes, which are these circles here. Nodes are just different weights and biases that check to see what properties of your input data are important for ending up getting to an output prediction. So we input the photoluminescence data, and multiple nodes of the first layer check out all the different weights and biases of the next layer. And then each node in that layer checks out all the different weights and biases of the next layer. And the neural network sees which path leads to the most accurate temperature prediction. So with that being said, there are different hyperparameters that you as the coder can manually adjust within your neural network. Hyperparameters are things like how many layers does your neural network have? How many nodes within each layer? What type of activation functions? How many times are you running the data through the neural network? S- Things as simple as that. And so there's a lot of playing around with neural networks in that manner, and also a lot of different combinations that you can get. So we had to run the data through multiple times with multiple types of neural networks to see which specific neural network with the hyperparameter combination gave the best accurate temperature prediction, or I should say the most accurate temperature prediction. And we got some pretty good results. So we did an 80-20 training test split. So 80% of our data was used to train the neural network, and also 20% of our data was used to test the network. And testing and validation are simultaneous with each other in this given instance. So we can see that of the 80% of the data used to train the neural network, there was only 0.3 degrees Celsius error, which is pretty good because it gives us a fairly linear graph. And also our validation data, which is simultaneous for testing, was 20%, and we also only got 0.3 degrees Celsius error, which is also good. It's nice to see those two match up so well. And that's this main linear function that you see right here. And it's hard to see, but there are little outliers that are responsible for the holdout data, which is 0.6 degrees Celsius, which isn't as good, but still pretty good. The holdout data was just data that we withheld from the 80-20 test split to just do an extra verification on how well the neural network makes predictions. So all in all, these are fairly good results. However, part of the reason why we use quantum dots is that because there are so many different types of quantum dots available. And what I mean by that is that quantum dots can be comprised of many different chemicals, molecules. Like, for instance, we used cadmium telluride, but there are plenty of other quantum dots options. And even of the cadmium telluride, there are different sizes of the quantum dots that we could have used that would have ended up altering the photoluminescent properties given off. So this is something to consider as we look towards the future. Also, when recording data, the quantum dot sample is held in a microfluidic device that helps to heat the quantum dots and change them as a function of temperature. So we're all also trying to optimize the microfluidic device also. Getting the optimal amount of use from our research is important because potentially this could be applied to treating cancer in terms of monitoring a cancerous tumor to make sure that only the tumor is being destroyed and not also the surrounding healthy tissue. So, with that being said, I'd like to thank you for your attention and ask that you have a great day. Thank you.